All right, thank you for coming. I'm Paul Dauenhauer from the University of Minnesota, and my background is mostly in reaction engineering and catalysis. I come from a department of chemical engineering and material science. We work in the areas of biofuels, renewable chemicals, and reactor design. And the problems I've come across have kind of forced my research not only to include those traditional topics, but also to kind of bleed into areas of analysis and analytical chemistry. And so just to give you an idea of what I'm talking about, a lot of the work we do in catalysis and reaction engineering is focused on very simple chemistry where we do what's called model compound studies. So we'll take something like linear alkanes and study the branching kinetics. And we can do that with single compounds, very well-defined reactions that are easy to study. Now, if we're interested in something like interactions, we'll go to mixture chemistry. And this might be something like 5 to 50 compounds where we can mix alkanes, aromatics, cyclic compounds, and study the interactions on surfaces. The problem is the complexity going from here, model compound, to mixture chemistry is quite big. To go from mixture chemistry to real systems, or what we call big chemistry, is almost overwhelming in terms to the point of being intractable research problems. And these are problems that reaction engineers, catalysis people want to study, but the analytical needs to be aligned with that. The problem is very simple. If we have, let's say, 1,000 to 10,000 molecules in our mixture, and we have millions of reactions, computational techniques can now describe millions of reactions. So if we have reactions happening on surfaces, gas phase, and solid phase reactions all happening together, we can track that. But the problem is we can't take those complex million-step reactions and align them with analytical reaction approaches. So it's difficult to quantify this many, and you think about it, even if I could separate all of those with 2D chromatography, the problem is if I have 1,000 molecules times 5 hours to calibrate, I can spend all of my time just calibrating all of these mixtures and identifying them. And you can be completely overwhelmed by the complexity of something like gasoline, which is something we definitely want to have a good characterization of. So moving forward, just to look at some exact problems we're talking about, you can take biomass or any sort of waste and gasify and make methanol. And then methanol you can take and do methanol to hydrocarbons, methanol to olefins. These are two interesting areas right now because natural gas is so cheap. But when I do that, I get a very complex chromatogram of hundreds of compounds, too many compounds to calibrate accurately and regularly for, such that it's really difficult to characterize the mixture, the distribution of products that I'll make. I'll still make C1 products, at C2, C4, C6, all the way up to C8s, and even bigger if I keep going, depending on the way the chemistry proceeds. And I'll give you another example here. Here's another renewable technology. If I take dry biomass, such as grasses or trees that exist throughout Minnesota, I can take those big biopolymers, rapidly heat them, I'll fracture the biopolymer, and then I'll quench it really quick. So the reaction time is less than 2 seconds of gas phase. Then those biopolymers break down to something volatile, but not all the way down to C1 chemistry. That's called biooil. And it's conceptually similar to petroleum in that we now have a bio-crude liquid which we can upgrade to fuels, consumer products, chemicals. And this is an approach that companies such as Shell and Exxon and others are looking at right now. The problem is the analytical challenge here is completely overwhelming because now, again, we have hundreds of compounds. As you can see here, this is a chromatogram of just one extracted fraction of that, the carbohydrate fraction. And not only do I have this many compounds in a fraction of that petroleum-like mixture, this bio-oil, if I look at the compounds here, they're extremely complex because they're so over-functionalized. You can see this is a molecule they call levoglucosan. It's sort of like glucose, but it's missing one water. It has this extra bridge. You have a lot of products like this, furan, that have a furan moiety, but then also 1, 2, or even more functionalities. C2s that are very light and reactive, and all of these pyran species. And again, this is just the carbohydrate fraction from cellulose. So why is this so difficult to do, and how can we solve it? This is what we were thinking about a couple years ago, having coffee and discussing it. And actually the problem is very simple. If you look at the way flame ionization detection is conducted, you take a sample, inject it, and it's separated into individual compounds. Those compounds are then injected into a flame where they can produce specific ions that are detected within the system. And really the problem when you think about it is if every molecule that comes in produces a different amount of CHO plus ions per molecule, then you get a different response for every molecule. This is why we have to calibrate. So some compounds give a very nice number of CHO plus ions, and some give very little. And then those are the ones we really have to calibrate very carefully for. The problem really, when you think about it, is that we're putting too much information into the detector. The molecules, all we want to know once we've identified them is how much carbon is in it, because from stoichiometry I can back out how many moles of the molecule. So what I really want to do is eliminate some of the information that's going into my flame. And it turns out conceptually that's very easy to do. And I can use this universal or quantitative carbon detector. Every molecule that comes out of my column can go through a universal methanizer to produce methane, and then that can go to the FID, where now no matter what compound went in of those 9 compounds, the carbon goes through as the same molecule, and I get the same response per carbon atom. I've eliminated that structural information that affects the formation of the ions. Now that's conceptually very simple to do, and I'll show you how we do it in a minute, but there's a significant benefit to doing this. Now my FID signal, once I do this, I still get the same separation I've had before, nice, clean, simple peaks, and the response factors for number of carbons all match up to unity, just as we would expect. But there's a benefit that now this is very repeatable in that every single compound gives me the same response factor, so I don't have the potential for calibration error or mistakes in my analysis as I proceed, in addition to many other benefits of time and cost of standards and standard storage. So how do you do this? It's conceptually very simple. It's the implementation that's difficult. For every analyte that comes out of my column, I pass it through a single chamber where I mix it with air, and I mix it with a catalyst under just the right conditions that I get full CO2 conversion to CO2. Then I take that CO2 and I do a full methanation in a second catalytic chamber. And if I do this right, I'll get over 99.9% conversion to methane, which then goes to the FID. So the way the system works on the inside is a coupled chamber of catalytic chemistries, where we go into one chamber where it mixes with air, through the other, mixes with hydrogen, and then back out to the FID. The challenge is to make this chemistry happen such that we achieve 99.9% conversion to methane or higher. And number two, we've just gone through all this effort to give nice, exquisite separation of all of the molecules with nice, sharp peaks. So what we don't want to do is a catalytic reactor that has either mixing or strong adsorption effects that are selective for any of the compounds. In other words, if I have nice peaks going in, I should have nice peaks coming out. And the way to do that is to use this 3D printed metal microreactor approach, where you can eliminate both of those effects and give you nice, clean peaks. So in here are 2 chambers and a heating source, just like conceptually this diagram shows, and this can be used in your GC. Now, the question that we had at the beginning is what catalysts, what conditions, and how do you know you can, for every compound you work with, you can achieve this 99.9% conversion? And you can do this kind of an approach that's similar to catalytic reforming, and you can get insight from that. If you think of in any of these catalytic systems, you have some distribution of carbon, hydrogen, and oxygen, and you can think about what conditions are very strong for methanation. So if you haven't seen one of these ternary plots before, you can just think of it this way. If all the compounds go into a single pot, I can add up how much carbon, hydrogen, and oxygen they are, and place those molecules somewhere in this 3-parameter space. So it turns out all the molecules that we're interested in, anything you can think of with carbon, hydrogen, oxygen, even sulfur, silicon, whatever you're working with, show up here in this tiny little box for the flow conditions we're talking about for this universal carbon detector. And what I can then do is ask, under what regions of this diagram, for the temperatures and mixture ratios that I have, do you achieve 99.9% conversion to methane? And the answer is it's actually dependent on the temperature. So I can plot here, as a function of temperature, a bunch of lines associated with this methane conversion, and everything that's above these lines in the gray here achieves that metric of methanation. There's another line I need, which is the combustion line. So if you're to the left of that, you have enough oxygen that you'll achieve complete combustion in the first chamber. So there's a nice design optimization problem. I want very high temperatures for favorable kinetics, but as my lines slip up here, I get less space where I can achieve my selectivity metrics. So that it turns out you want to be somewhere here, kind of in the middle, and then if all your compounds that you would potentially ever work with are way up here, you can guarantee that if the reaction goes to completion, you get complete conversion to methane. So you need an aggressive reforming style catalytic system. Now if you do this, you can take a bunch of compounds, many of these are similar to the ones I was talking about earlier, these highly oxygenated ones, and I can look at them whether using the conventional FID approach, like you see here, or I can use this QCD approach you see right here. And if I do the calibration, I get the exact same answer whether I use the conventional approach or the QCD approach. You can see here if I compare the QCD approach in blue, I get the response factors close to the same for all compounds, whereas the calibration has to be applied for all the exact same compounds by the conventional FID approach. And you can do all sorts of reactor studies where I'll look at the extent of mixing in this type of system, and I'll show you in a little bit that that's essentially negligible. So when you take this device, so this went then to the company, and they took our prototype, which is more crude, and they added a bunch of innovations which the company can tell you about, and a way to implement with a GC. All those things are more company, not as much the research that we do. So it sits in the GC right here, you inject, goes through the capillary column, then through the microreactor with its flows, and then into the FID where you get your signal. There's a temperature control built into the board. So it's fully automated once it's in place. So I have students that work with this system and do different experiments, injecting different things, evaluating its performance, its extent of kinetics, and all those sorts of things. One of the things we look at is its performance with different molecules and with time. So here's an example of a data set where I have a large number of molecules. So I can start working with alcohols or chlorinated species, amines, carboxylic acids. I can switch to mixtures that you see right here. And you can see here these are thousands of injections over time that the system remains robust. In fact, what's actually interesting about this is we started to see this pattern. You can sort of see here they look like little bumps. And what was actually happening was over 1,000 injections or a couple hundred, the samples actually start to degrade. And you can see that slight trend here in the data. And every time you replace a bottle, it goes back to perfect. So the problems are actually more with the sample preparation, which is something that actually we see throughout these types of systems. So we've looked at a large number of molecules. I have a lot of undergrads and graduate students that look at many of these different types of systems. You can see things here like pyridine, nitrogen-containing heteroatoms, all sorts of oxygenates, and even sulfur-containing compounds I'll say something about in a bit. One thing we had a really good undergrad that worked on was interested in the idea that we could use this to look at silylated compounds that are very difficult to work with and detect. And one we're interested in is this molecule FDCA. If you're familiar with PET plastic, this is plastic with the renewable recycling logo number 1. That's terephthalic acid, where you would have C6 aromatic ring right here in the middle. Companies around the world are trying to make this molecule renewably from biomass, and so there's a lot of interest in characterizing it. So you can do this and do a silomethylation preparation, inject it into a GC, and then quantify the total amount that you produce. There's many other things like drugs, food flavoring, or food just itself, such as glucose, that are interesting. And if you take this approach, you can do this exact same evaluation in blue, the Polyarc approach, and in red, the conventional FID approach. And for a lot of these things like vanillin or drug compounds, you have a very low response. You dramatically enhance your detection of this by the universal carbon detection. Now there's even molecules that are worse. If you look at some of these other things like carbon monoxide, carbon dioxide, or formic acid, this one is really important for biomass applications. You can then compare these with the Polyarc approach versus the conventional FID. And here what you see is where you get a very nice response with this microreactor FID approach. For some of these, they're essentially invisible. Carbon monoxide and carbon dioxide are essentially undetectable. Formic acid is almost undetectable when some of these have almost no response. So if I look at the two chromatograms side by side, here in blue, you can see all of the species that show up because they now are fully methanated, and on top, only a couple that you would anticipate give some response. And now you can see what I was talking about earlier. When you use this 3D printed microreactor approach, you get this nice resolution and very nice peaks remaining with a negligible shift in the GC. Okay, you can see this too when you look at this a couple of other ways. There's other peaks here, and you can actually look at the measured concentration versus the actual concentration. You get this nice parity between the two with the microreactor FID, whereas in a conventional system you do not. Now finally, the last question I'll kind of leave you with here is what's the effect of sulfur? Because a lot of the fuel mixtures we work with have heteroatoms that are very strong poisons for catalysts. It's a natural question. What's the role of sulfur on the microreactor system? And it's known in reforming chemistry that these can form surface poisons that are very difficult to remove and almost impossible to regenerate. So what we started looking at was we could take one of these microreactor systems and sequentially pulse it with different amounts of sulfur. And you can see here, this is the amount of sulfur we've injected. And I'm presenting it that way because we've injected different amounts, you can see with time. We started out with 200 ppm sulfur, then we went to 0.2 weight percent, then we went to 2 weight percent, and finally 10 weight percent sulfur in the form of biofenes. And then you can get the relative response factor for each of these. And you can see you sit right here nicely at the relative response factor relative to methane of 1 for a huge amount of sulfur, 0.6 milligrams. And it turns out that the capacity of the system is sufficiently large that it extends way beyond the lifetime of the reactor for almost every single application. And if you look here at something like marine engine oil, you're up, that 0.6 milligrams of sulfur would be the equivalent of about 10,000 injections for a very common injection volume. And even something like ultra low sulfur diesel, as it's going to even lower standards, is somewhere between 100,000 and 1 million injections. It's not until you get down to very sour crude oils where it's huge percents of sulfur that you get into the 100 to 1,000 injection range of interest for this type of application. So the capacity is there to work with sulfur species, which is very useful for the types of big chemistry applications I was talking about at the beginning. Okay, so let me summarize here real quick. I think I went over a little bit. But the UCD provides calibration-free analysis of organic compounds, which is really useful when you want to merge the analytical world with the reaction and catalysis world, because I can tell you, catalysis people and reaction engineering people, they don't want to spend any time on analytical work. They just want to, know what the molecules are, and they want to just get past all of that. I know that's weird for analytical people to hear. It integrates with conventional separation techniques, so you don't have to do anything special other than basically plug it in. It sits there, it operates by itself. It has huge application space, fuels, heavy compounds, food, ingredients, drugs, invisible compounds, and sulfur-containing compounds. And like I said, it just makes working with huge complex mixtures extremely simple unless you focus on your research. And let me just conclude here by saying this work was funded by the U.S. Department of Energy Frontier Research Center program from Basic Energy Sciences. So thank you.